Okay, lecture 29. Ionic theory of solutions and solubility rules. Here's some terms you should know. And then we're going to start with the solubility rules because that'll help us with some of the later problems. You have a table of solubility rules. It's not complete. We had the full solubility rules table. It could be, I'd suspect that'd be hundreds of pages, but what's nice about this is that when we're dealing with ionic compounds, this solubility rules table covers the vast majority of the compounds we will normally come across in lecture or lab. So let's go through these problems. We have the first one here, lithium selenide. Now what you want to do is, first you should have these memorized, but very quickly for at least the first two rules. That we have, the first rule says that if we have lithium, sodium, or potassium, or ammonium ion, any of those ions that are part of a compound, it is soluble. We don't even need to know what this is. Could have come in and covered it up and you just saw that it has lithium in it, it's soluble. Done. Lithium, whenever it's lithium ion, I should say, whenever it's attached to something, makes it soluble in water. The second rule, and if this had been sodium selenide, same thing. As soon as you see that sodium or potassium or ammonium ion attached to anything, definitely soluble. Now the second rule, or second problem here, copper 1 acetate. Big thing is you have to know what you're dealing with as far as the polyatomic ions. That's acetate, and that's rule 2. It says anything that's attached to acetate is soluble. So this is soluble. And again, you wouldn't even need to know what's attached here. You just see the acetate is attached to something, then it must be soluble. And then also ammonia, we have acetate and the nitrate ion. So if you have something like, let's see, if we have tellurium nitrate, oops, something like that. As soon as you see the nitrates, doesn't even matter what this guy is. Actually, it would be like technetium. No matter what crazy thing is attached to it, if it's nitrate, it's soluble. Now, we have silver bromide. So we have silver and the bromide. If you look in the solubility tables, we have no rule for silver ion, just on its own. But what we see is that bromide, anything attached to bromide, is generally soluble, except certain compounds, including silver bromide. When bromide is attached to the silver ion, it is insoluble. So let me circle these here. So you should know that bromide, chloride, fluoride, those, when they're attached to something, generally speaking, they're soluble, but there are exceptions. So if you look at the table, you have your rule, and then you have your exception. And there's very few exceptions, but they're important to know. So we go to the next one, calcium sulfate. Look, for the rules, there's nothing about calcium, but there is about sulfate, and the sulfate rule is that most sulfates are soluble. So then once you've checked that, you should know the exceptions, and one of the exceptions is calcium sulfate. So if you had, let's see, gotta find something, say hafnium sulfate. Well, there's nothing about hafnium in the tables, even as exceptions, so you'd have to assume that this is soluble. But sulfates are generally soluble except for calcium sulfate, strontium sulfate, barium sulfate, silver, mercury, and lead sulfates. So you should know those exceptions. Now we have tungsten 4 carbonate. Carbonates, most carbonates are insoluble. Well, if that's the case, then also you should know the exceptions. The exceptions are group 1A carbonates and ammonium carbonate. Well, tungsten is not a group 1A metal, and it's certainly not ammonium ion, so this would be insoluble. So we go with the rule, but you should also know the very few exceptions, and they have a tendency to follow a trend. Group 1A, if you look at the exceptions, you'll see group 1A and ammonium are exceptions for the generally insoluble anions. Phosphate is insoluble, but it's attached to sodium here. Sodium, and that's why the rule about sodium is rule number 1. it is the most important rule, so or it supersedes the one about phosphate. So if you have sodium, there are no exceptions to that rule. If there's sodium attached to something, it's soluble. So phosphate is insoluble, but the exception is group 1A ions. So this is soluble. Okay, make sure we're on the page. And then we have scandium sulfide. Sulfides are generally insoluble. Is scandium one of the exceptions? Nope, just group 1A and the ammonium ion, so this is insoluble. And then hydroxides are generally insoluble, except for group 1A hydroxides, calcium, strontium, and barium hydroxides. This is vanadium hydroxide, so insoluble. Just want to go back real quick to make sure as I'm saying this. Yep, everything's good. Go to the next problems. Verify here. Okay. And we have sodium dichromate. Well, sodium doesn't matter what it's attached to. Soluble. Done. Nitrate doesn't matter what it's attached to. It's soluble. Done. Those rules have no exceptions. So there's no hemming and haw here. Bromide, though, that's a halogen. That's a halide ion. We know there are exceptions. This is cobalt-3 bromide. So we go to the table, and we see that silver, mercury, lead show up as counter ions that will make them insoluble. So bromides are generally soluble. This is not one of the exceptions, so this is soluble. Ammonium ion, soluble. Done. Stop looking. You don't even have to go any further. See, ammonium. Now, you have the carbonate that's insoluble. You can certainly should know the rule that carbonates are generally insoluble except when they're attached to group 1A or ammonium. Then we have aluminum phosphate. Phosphates are insoluble. Aluminum is not one of the counter ions. That's the exception, so this is insoluble. Cadmium sulfide. Cadmium is not one of the exceptions, so it is insoluble. So you need to know the rules and the exceptions. And again, the exceptions, there's seemingly a lot of them, but if you look at them, you see that really there's not that many. Silver, mercury, and lead come up a few times. Calcium, strontium, barium a few times. Group 1A and ammonium ion come up several times as exceptions. So just make sure you have these rules under your belt. You'll be fine. Barium hydroxide. Barium hydroxide is a strong base, so you should know that it is soluble, but it's also one of the exceptions. Mercury 2 iodide. Iodides are generally soluble except when attached to mercury 1 or mercury 2. And so this is insoluble. Sodium nitrate. Now this one is a super soluble. Sodium ion is soluble with whatever it's attached to. Nitrate ion is soluble with whatever it's attached to. So definitely, you don't have to put super soluble, but it is. Zirconium nitride. Do we have a rule for zirconium? No. A rule for nitrides? No. Now if you looked up on the internet, you'd find that you could probably find the solubility of zirconium. I guess it's zirconium 3 nitride, but we don't have a rule for it, so you'd have to say something like can't be determined. Not with the rules that we know. The rules are out there, but we don't know them. So I just put that in there to show you the solubility rules table. Doesn't cover everything, but it covers quite a bit of what we normally deal with. Okay, number 2, determine which of the following are electrolytes and which are non-electrolytes. So electrolytes are going to break up into ions and create a fairly strong current. This is an ionic compound, so this would be an electrolyte. This is a molecule. Now, we don't know too much about molecular compounds right now as far as what's soluble and what's not. The rule is like dissolves like. And we don't get into polar versus nonpolar molecules till much later in the chapter. But you should know that methanol is one of our compounds that we have a name for from the organic compound lecture. So this methanol, and it dissolves in water, so it would be a non-electrolyte. Even though it dissolves in water, it doesn't produce ions, so we don't get an increase in the current that we can put through that solution. Next one is sucrose. This is generally given as the most common example. Sucrose, table sugar, dissolves in water very readily, but it doesn't produce ions, so we don't get an increase in the, or reduction in the resistance of the solution, so we don't get a increase in the current. And then we have iron 3 nitrate. Nitrates are soluble. It means they break up into ions, so this is an electrolyte. And the final problem, determine which of the following are strong electrolytes and which are weak electrolytes. Now, this one, ammonium acetate, this breaks up into ions, so definitely it's an electrolyte, and because it breaks up completely into ions, because the solubility rule says that they break up into ions, that's why they are soluble. So these are strong electrolytes. And I should say that the solubility rules for ionic compounds, what they're telling us is if they are soluble, they like to break up into ions. If they break up into ions, they allow a strong current to go through the solution. Copper 1 sulfide is insoluble, so we'd expect this to be a weak electrolyte, maybe even a non-electrolyte, depending on how much it may break up into a few ions, but not very much. Ammonia is a good one to deal with because it comes up so much it reacts with water, and it produces ammonium ion and hydroxide ion, but very small amounts. So this would be a weak electrolyte. And then HCl is hydrochloric acid. That breaks up into ions readily, 100%, and so this would be a strong electrolyte. So you should know that strong acids and strong bases are strong electrolytes. Weak acids, weak bases are weak electrolytes. Insoluble ionic compounds are weak electrolytes or non-electrolytes. And then soluble compounds are strong electrolytes.